Hello there and good day. This is my presentation of the initiated chemical vapor deposition lab by me, Noah Khan. And let's get going. So for the introduction and motivation behind the chemical vapor deposition process, the process itself is really a subsection of thin layer deposition as a whole, and these techniques differ a lot and are very complex, and they can be split up into even smaller subsections when utilizing different types of deposition methods. The process analyzed by this video specifically is low pressure CVD, as the process is undergone in a vessel that is near vacuum and has no plasma assistance. And the motivation behind this experiment is for students, similar to myself, to gain insight on the nuanced aspects of the process, such as reaction kinetics, polymer chemistry, and vapor phase flow. With this in mind, we can take a deeper look into the methods. So here we have a very simplified overview of the CVD process, or rather the iCVD process. It begins with an initiator species being introduced into the system, where it dissociates because of thermal decomposition, as shown through the interaction with the heated filaments. And then the activated initiator is attracted to the surface, and once a monomer molecule meets it, they react and form product on the surface. Now, this process is said to have significant advantages compared to the other deposition techniques. It is conformal, solventless, and the process can allow for deposition of a film on nearly any surface, even paper or cardboard. Extremely gentle. So these are just some relevant equations to the data that we're going to be looking at in a second. And looking at it, for our intents and purposes, the really important ones are really how rate, activation energy, and the film thickness deposit per cycle are related. And also, as you can see, the lambda and nu values are set beforehand. Here we have some data that we had been given and was formatted by one of my colleagues. And when looking at it closer, you can see that these two trials that are depicted are very similar in that they have the same species of feeds, being hexyl acrylate and TBPO, and also the same flow rates for both of those. But the only difference, at least in the set variables, are the stage temperatures, with the first trial being at 24 degrees Celsius and the second trial taking place at 26.2 degrees Celsius. So here we have that same data that we took a glimpse at before, but now in graphical form. And in this form, two obvious observations can be made. When looking at these waves, we can think of every peak as being a cycle of deposition, or the deposition of a single layer. And counting the peaks between the two trials, it becomes obvious that in both trials 5 layers were deposited. The difference, though, between these two, and that being the second observation, is that in the first trial, at 24 degrees Celsius, the process took 11 minutes in order to deposit 5 layers. Whereas in the second trial, at 26.4 degrees Celsius, the process only took 8 minutes to deposit the same amount of substance. With that being said, the deposition rate can be said to be directly proportional to the stage temperature. And in other trials, an increase in flow rate was also directly proportional to the deposition rate. And an increase in flow rate of incoming species, whether that be the monomer or the indicator. Now, from these observations, we can conclude that a higher temperature or higher flow rate leads to a higher rate of deposition. And then looking at the three equations printed below, we can see that a higher deposition rate, with all other variables held constant, means that the deposition was increased because of a decrease in activation energy, or rather a temperature increase, giving enough energy to get across that activation energy. Well, this was my presentation on iCVD, and have a wonderful day.
Have a wonderful day.